Hello again. We are continuing chapter 10 with 10.2. Now we know what parametric curves are. Now we're going to perform calculus with those parametric curves, and we will be looking at tangents to those curves, areas created by those curves, the arc length on the parametric curve, and the surface area on the parametric curves. Let's start with tangents. And we know that the tangents always involve the derivative. I can determine the tangent line, of course, to a curve, knowing a point, let's say point A comma B, right? And we determine the slope of the tangent line, and of course, y minus b equals the slope x minus a. So the point will be given to us, or we have to determine it, and in order to find the tangent, we will have to use the point slope form with the point that we determined or it's given to us and the slope. Okay, so we know that parametric curve, any parametric curve, is defined by x, a function of t, and y, another function of t. Also, these are differentiable functions. Differentiable. Differentiable. Good. Also, y is a differentiable function of x. Diff function of x. Knowing that, if we want to determine, so y is a function of x, but x is a function of t, right? So when we want to differentiate and find dy over dt, we have to use the chain rule. So we first differentiate with respect to x, so dy with respect to x, and then we differentiate x with respect to t. This is a long time known rule, right? The chain rule, it comes from Calc 1. Well, what we're interested in is determining this. So what I have to do is divide by this quantity. So in order to find dy over dx, I will have a ratio of dy over dt over dx over dt. So why do we need this? Because we want to determine the slope of the tangent line to the curve at a particular point. And of course, the curve is a parametric curve. Now, at this point, few topics here that are very important. For horizontal tangents, obviously the numerator has to be 0. dy over dt has to be 0, but dx over dt cannot be 0. Okay? Not 0 over 0, just 0 in the numerator. Now, let's say for vertical tangents, that's my page 2. So what happens for vertical tangents? Then for vertical tangents, the denominator has to be 0. So dx over dt equals 0. But dy over dt cannot be 0. Again, not 0 over 0. In the situation in which dy over dt and dx over dt are 0, we cannot make a conclusion. We have to use different methods. No decision, no conclusion about the tangent. Okay, now one more topic here is the second derivative. Before we look at applications. The second derivative is d2y over, of course, over dx2. And how do we determine this? So let me copy the dy over dt here, dy over dx, of course, which is dy over dt over dx over dt. This is what we just wrote on the previous page, this. And how do we get this? Well, all we have to do is remember that this is d over dx of dy over dx, right? The second derivative with respect to x of the first derivative with respect to x. And all we need to do to understand how this is obtained is replace in this piece, replace this. Okay? So then d2y over dx2 is nothing else but d over dt of dy over dx and everything over the same thing, dx over dt. And you may wonder, why do I need a second derivative? The second derivative is important for, as we know, concavity. If the curve opens up, then d2y over dx2 has to be positive. If the parametric curve opens downward, of course, the second derivative has to be negative. I think we're now ready to look at examples for tangents. So right now we are talking about tangents and later on about areas, arc length, and surface area. So I am on my page 3. Good. So let's look at a few examples. I'll start with a very simple one from the recommended ones by the math department. So 3 on page 679. And we are given x equals t e to t, and we're given y equals t plus sine t. So this is the f of t and this is the g of t. So in this problem, we're asked to find all the derivatives, dx over dt, dy over dt, and then the ratio, of course. So let's start with dx over dt. It's a product. I have to use the product rule. So we get e to the t plus t e to t. And let's determine dy over dt, which is 1 plus cosine t. In order to determine the derivative of y with respect to x, we know the formula is this over this. So it's 1 plus cosine t over e to t plus t e to t. And we don't have to do anything else to it. Okay, let's look at problem 7 on the next page, which is 680. Find an equation of the tangent to the curve at the point corresponding to the given value of the parameter. So we have x, a function of t, which is t to the third plus 1. And we have y, another function of t, t to the fourth plus t. And we are given t equals -1. Okay, so they want us to determine the equation of the tangent. Well, the first thing I need to determine is the point x comma y. I have t, which is -1. -1 cubed is -1 plus 1 is 0. And 1, because -1 to the fourth is positive, 1 minus 1 is 0. So they're really asking us to find the equation of the tangent line to the parametric curve passing through this point. So then we have y minus 0 equals the slope x minus 0. All I need to determine is the slope, which will be dy over dx evaluated when t equals -1. This is the whole question here. Once I have this number, I plug it in. Good, so I have to find dx over dt. dx over dt is 3t squared. I have to find dy over dt, which is 4t to the third plus 1. I have to find the ratio and plug in -1. I'm going to move on to page 4. So dy over dx equals 4t to the third plus 1 divided by 3t squared. And now I have to evaluate this when t equals -1. t equals -1, this will be -4 plus 1 over 3. -3 over 3 will be -1. Now I can go back and plug it in. Y equals -1 times x. So this is the equation of the tangent line to the graph of the parametric curve given by x and y, functions of t, at the point 0, comma 0. Okay, let's look at something else. Let's say 17. On the same page, 680. The question is asking us to find the first and the second derivatives, dy over dx and d2y over dx2, and for which values of t is the curve concave upward. So they're asking us the values of t for which the curve is concave upward. Okay, so let's take a look. So we have x equals e to t and y equals t e to negative t. Okay, so in order to find dy over dx first, we have to find dx over dt, which is e to t. We have to find the dy over dt. It's a product rule, careful here. So first function prime is 1, e to negative t, minus t e to negative t, because when I differentiate this, I get negative e to negative t. So finally, we have dy over dx, this over this. So e to negative t minus t e to negative t divided by e to t. To simplify a little bit, first of all, I will factor out e to negative t, and then I have 1 minus t in parentheses. I can bring this down and multiply, copy the base, and add the exponents, and also factor out negative 1. So e to 2t. Yes, it can be written as negative t minus 1 e to negative 2t. Either one. Good. So we determined the first derivative, but for concavity, we need to find the second derivative. So let's do that. So d2y over dx2, remember what this means. It's d over dt of dy over dx, which is this. So maybe because I don't want to use nested parentheses, I'm going to put the negative 1 back in. So, well, I have to use nested parentheses anyway, so let me just leave it alone. So negative t minus 1 e to negative 2t, and divided by dx over dt, which is e to t. Give me 1 second to get rid of the extra not needed parenthesis here. Good. Good. We continue. We have to differentiate this as a product. I will leave the negative outside. And 1 over e to t. And now I'm differentiating t minus 1 prime is 1 times e to negative 2t. And then plus, because the negative is outside, plus t minus 1 and e to negative 2t and times negative 2, the inner function prime. We're going to try to simplify this. I'm continuing on the next page. Where is it? Okay. 5. Okay, so let's see. This is like negative e to negative t. I will factor out, of course, e to negative 2t. This is a 1, but this is a negative 2t plus 2. So we factor out e to negative 2t, it's outside. I have 1 from here. This is out. I distribute negative 2 to t and negative 2 to negative 1. So negative 3t. And this is negative 2t plus 3. Negative 2t plus 3. And now I'll put the negative back. And I have negative 2t minus 3 over e to 3t. Perfect. So now, if this is positive, or when it is positive, the function is concave upward. When it's negative, the function is concave downward. We are only asked to determine this. This is a quantity that is always positive. We shouldn't even look at it. So for the whole fraction to be positive, the numerator should be positive. So 2t minus 3 greater than 0 means t greater than 3/2. Or I will say, on the interval 3/2 infinity, curve is concave upward. We're not asked to determine the other if it's when it's concave downward. But of course, it will be from negative infinity to 3/2. Okay, let's see if we have another tangent here to work on. Yes, we do. So let's take a look at what is it? 21 on 680. So the question states or asks, find the points on the curve where the tangent is horizontal. So horizontal tangent and vertical tangent, and the points. They want us to determine the points for the horizontal and vertical. Perfect. And we have x equals t to the third minus 3t. And we have y equals t squared minus 3. So first of all, we have to determine dy over dx. So first the dx over dt, which is 3t squared minus 3. And then dy over dt, which is 2t. Now, of course, dx over dt, which is this over this, 2t over 3t squared minus 3. Very good. So now we know that dx over dt is, dy over dx. Sorry about that. So dy over dx one more time, so I don't want to confuse you, is 2t over 3 over dx over dt, which is 3t squared minus 3. So dy over dx is 0 for the vertical tangent, but I have to make sure that 3t squared minus 3 will not be 0 for that value of t. So this is first for the vertical tangent. When is this fraction 0? Only when t is 0. Is this quantity 0 when t is 0? No, it's not. I get negative 3, which is not 0. So when t is 0, this parametric curve has a vertical tangent. Of course, I meant horizontal. So when the derivative is 0, the parametric curve has a horizontal tangent. So yes, it's 0 when 2t is 0 or t is 0. Make sure that the denominator is not 0, and it's not. For a horizontal tangent, I can find the point because we are asked to find the point. When t is 0, this is 0, x is 0. When t is 0, y is negative 3. Okay, now on the next page for vertical tangent. Vertical tangent is when the denominator is 0. So for the vertical tangent, then this fraction is undefined. So dy over dx is undefined. When is it undefined? When 3t squared minus 3 is 0. And of course, we know that t equals plus or minus 1. I subtract and take the square root or factor. So now I have to make sure that the numerator is not 0 at this point. So 2t is not 0 when t is 1 or t is negative 1. So we are safe. So now I have to find the points. So when t is negative 1 and when t is 1. So let's see what the point will give us. What point will we determine? So for t equals negative 1 is negative 1 but plus 3. So that is 2. When t is negative 1, this is 1 minus 3, which is negative 2. Now let's determine, so again, this was for the vertical tangent, when the denominator is 0, or the derivative is undefined. So t equals 1. 1 minus 3, so it's negative 2. And then 1 minus 3 again, still negative 2. Very good. The next video will continue with the other applications in a minute.